Okay, we're in section 3.10 and we're talking about differentials. On the first page is just some terminology and some notational stuff, and then I described what we mean by dy and delta y. Dx and delta x mean the same thing, it's just the increment that you are away from x. Dy is the rise-fall distance on the tangent line. Delta y is the rise-fall distance on the curve. Okay, now if dx is small, then dy and delta y would be very close to each other, roughly. Now they're not going to be exact, okay, so it's important that we use the approximation sign here and not the equal sign. Here's an approximation formula that we're going to be using later in the video. So, okay. Problem 5, I want us to compare the values of delta y and dy if f of y equal f of x equal 5x minus 7 divided by x minus 1. And x changes from part A from 2 to 2.28, and then part B we're going to compare these as x is going from 2 to 2.1. Okay, so here's a picture of the graph of this function. Now, 2 and 2.28 are very close to each other, right? Same thing with 2 and 2.1. So in part A, my dx value would be 0.28. Okay, now notice that again, if I'm a small increment away from this x value, okay, x is 2 for this problem, the gap between the curve and the tangent line is going to be very small. So when I compute delta y and dy, in a problem like this, I should kind of know early on that these two numbers are going to be very, very close to each other. Okay, not equal, but they're going to be very close to each other. So let's go ahead and find the derivative, since we'll need that in the calculation. It's going to be a quotient rule. Okay, f prime of x, we need the bottom, which is x minus 1, times the derivative of the top is 5, minus the top, that's 5x minus 7, times the derivative of the bottom, that's 1, all over the denominator squared. Simplify that in the numerator, I'll get 2, and then divided by x minus 1, the quantity squared. Okay, now x for this problem is 2. F of 2 would be 3. Excuse me, I'm pointing the wrong thing here. Sorry. F of 2, I'm going to plug that in here. 5 times 2 is 10, minus 7 is 3, divided by 1 is 3. Okay, now f of 2.28, if you were to plug in that number here, you should be getting 3.4375, and that's an exact. Okay, now we want to find delta y. Delta y is the rise-fall distance on the curve. Okay, and we find that by computing f of x plus delta x minus f of x. Delta x and dx are the same thing, and for this part here, delta x would be 0.28. Okay, so f of x plus delta x, 2 plus 0.28 would be 2.28. And then I'm supposed to subtract f of x, x is 2, so delta y would be where I just simply take f of 2.28 minus f of 2. Again, I'm using that formula here. And I end up getting, so these two numbers are known, right? Here's, take this number minus this number, and okay, I'm getting 0.4375 then for delta y. dy is where I take f prime of x dx. Okay, well here's f of x, right? And stick a dx at the end. Now x is 2, dx is 0.28, dx and delta x are the same, I mentioned. And so I would just plug these numbers into this formula here. X is 2, so you can have 2 divided by 1 times 0.28. 2 times 0.28 would be 0.56, and that's dy. Now these two values are very, very close to each other, In fact, it'd be a difference of 0.1225. That's very small. Okay, now before we look at part B, a distance from 2 to 2.1 is smaller than a distance from 2 to 2.28. So before I calculate anything here in part B, I would expect my answer to part B to be two numbers that are closer to each other than what I see here. Okay, since the gap is going to be smaller, since I'm not going as far away from 2 as I was before in part A. Well, f of 2.1, if you plug in 2.1 here, I was getting 3.181818, the infinite decimal. 3.18 repeated. Okay. Delta y is where I take f of x plus delta x. X is 2, delta x is 0.1. 2 plus 0.1 would be 2.1. Minus f of x, x is 2, so f of 2 is 3. Okay, 3.181818, the infinite decimal, minus 3 would be 0.181818, the infinite decimal. How about dy? Well, dy is where we take f prime of x dx, and we've already found that formula here. X is 2, and dx is 0.1. So I'm going to have 2 divided by 1 is 2, times 0.1. 2 times 0.1 is 0.2. Okay, now these two numbers, delta y and dy, are very close to each other. It'd be a difference of 0.018181818. Okay, now these two numbers are closer to each other than they were in part A. Okay, and I can see the difference there. Well, that's not surprising, right? That's something we expected, right? The gap is going to be smaller if you're closer to 2. Okay, so this exercise is really just a comparison between delta y and dy, and the fact that if you're not very far away from your x value, those two numbers are going to be very close to each other. Let's take a look at problem 6 next. Suppose that you need good approximations to these two numbers. How about the square root of 16.5 and then part B, 7.85 to the 2/3 power, but your calculator has died. Okay, use differentials to approximate each number. Well, let's see. So the first thing that we're going to need is a function. In part A, I'll need to let f of x be the square root of x. Since I've got the square root of a number, I'll let y be the square root of x. Okay, and I got to use differentials, so I'm going to need to find dy, and delta y for this problem would be 0.5. Because I know the square root of 16, that's easy, that's 4, right? 16 is close to 16.5. So you want to select a number, x, that you can know the value of, without a calculator here, is the idea. X is 16. dx is 0.5. Okay? dy would be where I take f prime of x dx. Well, here's f of x. F prime of x would be 1/2 x to the negative 1/2, or 1/2 root x, using radical notation, and then make sure that the dx is there. Now, x is 16, dx is 0.5. So if I plug those numbers into their appropriate spots here, which I've done on this point, I'll have 1 divided by 8 times 0.5. 0.5 is 1/2. 1/8 times 1/2 is 1/16. 1/16 in decimal form would be 0.0625. Okay. Now, I would like to know the value of the square root of 16.5. Of course, it's going to be more than 4, right? Because the square root of 16 is 4. Okay, but I need to get a good approximation of this number. Well, I'm going to be using this formula here. Okay, f of x plus delta x is approximately f of x plus dy. In other words, this distance from r to the x-axis is going to be roughly the same as this distance from point Q to the x-axis, as long as dx is small. You know, if dx is big, then yeah, there's going to be a big gap, and those aren't even going to be close. So it's important to note that, you know, delta x is, you know, a small number here. So yeah, I'm using that formula. I've written that again. And x is 16, delta x is 0.5, right? Because if I take 16 plus 0.5, I get 16.5. F of 16.5 would be the square root of 16.5. And that's what I'd like to approximate. Okay, well that number is going to be approximately equal to f of x plus dy. X is 16. dy, we've already said, is 0.0625. F of 16, well, that's 4, right? That's easy to, we don't need a calculator for that. So all I got to do is take 4 plus 0.0625. That'd be 4.0625. Okay, now the actual value, if you were to go to the calculator and type that in, the square root of 16.5 is what you see here. Okay, roughly 4.062. Okay, this looks like it's right on if you go nearest two digits, right, or nearest two digits, excuse me. Okay, but yeah, this is a good approximation, right, to what actually is the number. Now, just an observation. Suppose I wanted to know the square root of 16.1. They're not asking for that, but if I wanted to know the square root of 16.1, I would have a better approximation for that number than I would the square root of 16.5, because 0.1 is closer to 16 than 16.1 is closer to 16 than 16.5 is, right? Your dx value would be smaller, therefore having a better approximation. Still, this is a good approximation though, okay, but just an observation. Part B, we want to find the value, or approximate value of 7.885 to the 2/3 power. Okay, well, I need a function. I'm going to call this y equal g of x, and since I'm raising a number to the 2/3 power, let's let g of x be x to the 2/3 power. Okay, now I need a number x that I know x to the 2/3 power. Well, if x is 8 to the 2/3 power, 8 to the 1/3 is 2, right? That's the cube root of 8, and then squared would be 4. So 8 to the 2/3, that's 4. That's easy enough to get without a calculator. Now, dx would be negative 0.15. dx can be positive or negative if you're going to the left or to the right of that x value. I am 0.15 units away from 8, but I'm to the left of 8, right? I wouldn't want dx to be 0.15 because then that would get me an approximation for 8.15 to the 2/3, which I don't care about. Okay, I need to know 7.85 to the 2/3 power. Dx, therefore, is negative 0.15. Okay, dy is where I take g prime of x dx. Well, that's going to be a power rule, right? And 2/3 x to the negative 1/3 in radical form would be 2 divided by 3 times the cube root of x. Make sure that the dx is there. X is 8, dx is negative 0.15. So when I plug those numbers in their appropriate spots, which I've done here, okay, the cube root of 8 is 2. The 2's will cancel. And let's see, negative 0.15 divided by 3, that'd be negative 0.05 is dy. All right, now I'm using this formula. F of x plus delta x is approximately f of x plus dy. X is 8, delta x is negative 0.15. 8 minus 0.15 is 7.85. F of 7.85 is 7.85 to the 2/3 power, right, if I plug that number in here. And that's what I'd like to approximate. So that number is going to be approximately equal to f of x plus dy. X is 8, so I need f of 8 plus dy. dy is negative 0.05. F of 8 is 4. Okay, 8 to the 2/3 is 4. 4 minus 0.05 is 3.95. Okay, now the actual value, if you were to check that, is right here. So we're actually right on if you go nearest 2 digits. We're rounding. Again, this is a good approximation. Okay. Now, a couple things to point out. In a problem like this, problems like this, of course, on a quiz or a test, like I'd want to see this work. I'm not just asking you to go to the calculator and type in the square root of 16.5. Anybody can do that. I can show my first grader how to do that. Okay, that's not what I'm doing in the problem. I need to show how to approximate this number, and suppose I didn't have a calculator. Okay, well, I'm going to want to see this work here. Okay, now of course you can check your answer by going to the calculator and checking, but make sure that the work is there. Okay, that's what I'm looking for. Also, this may sound like a little thing, but in the calculation, it is extremely important that we use the approximation sign here, and not an equal sign. Some students will write an equal sign, and I will take points off for that, because we're approximating these numbers. Nothing is exact. Okay, the square root of 16.5 is not exactly 4.0625. It's an infinite decimal. Okay, so it's important that we use the approximation sign here in the calculation. Make sure that you're paying attention to that. All right, problem 7 is the last one on this worksheet. Suppose that we need a good approximation for cosine of 59 degrees, but you have an inexpensive calculator that does not provide the trig functions. You have some $5 Walmart, cheap calculator here. All right. Use differentials to approximate this number, and assume that the calculator can perform root calculations. We'll need to use that in the calculation, root functions. Okay, well, I'm going to let, this is going to be very similar to what we were doing up here. Okay, I'm going to let y equal f of x be equal to the cosine function cosine of x. Since I want to know cosine of 59 degrees, it makes sense to let the function be cosine of x. dy is negative sine x dx. Okay, now x for this problem would be 60 degrees, because I know cosine of 60 degrees, that'd be pi over, that'd be 1/2, right? 60 degrees is the same as pi over 3 radians. Cosine of 60 degrees would be 1/2, right? I've got that 30, 60, 90 right triangle. Dx would be negative 1 degree. Since I want to know cosine of 59 degrees, 59 degrees is 1 degree to the left of 60 degrees. Okay, and negative 1 degree in radian measure would be negative pi over 180. dy has been calculated already. X is pi over 3, dx is negative pi over 180. So I'm plugging those numbers in here. And sine of pi over 3, that'd be root 3 over 2. There's a negative in front of this, though. And I'm multiplying negative root 3 over 2 by negative pi over 180. Okay. Now, I'm using this approximation formula that we've been using here in these other two problems. And so x is pi over 3 radians, dx is negative pi over 180 radians. So f of x plus delta x would be f of 59 degrees, right? 60 degrees minus 1 degree. And so here's f of x, right? And I get cosine of 59 degrees. All right, that's what I'd like to approximate. Well, I'll be able to approximate that number. I'll make sure that you've got the approximation sign written and not an equal sign. I'll be able to approximate that number by taking f of x plus dy. Well, x is pi over 3. F of pi over, the cosine of pi over 3, that's 1/2. And then plus dy, dy is right here, pi root 3 over 360. Okay. Now we are able to assume that the calculator can do root calculations, like suppose it can, compute the square root of 3. Also suppose that it has a pi button on it. I guess if it doesn't have a pi button, you can always just use 3.14159 or something. You can approximate that number also. So now you can go to the calculator, the one that doesn't have trig functions, type this expression in, and you get roughly 0.51511499947. Okay, now the actual value of cosine of 59 degrees would be this number here. Of course, make sure you're in degree mode when, if you're to check this using the calculator. And these two numbers are very close to each other, right? They're right on if you go nearest 3 digits. So, what we're doing here is a good approximation method. It makes sense to be using this method as long as dx is small. All right, which for these problems, dx was a small number, and you can see when we're comparing what we calculated to the actual number, like it was very good, very close. Okay, now in this day and age, of course, problems like this are not really like something that we'd use a ton. Okay, but hey, technology does break down. Okay, like what if you're working at a job and your calculator did die, or you have this model calculator that can't do trig functions, and you need this right away. Okay, the boss needs it right away. Okay, well, here's an option that you could consider to at least get a good approximation, for certain numbers, certain calculations there. All right, we're all done with section 3.10. So be sure to look at the problems here that are on page 256. The odd numbered problems listed.